So welcome. My name is Patrick, and today I will present you Blacksmith, scalable rowhammering in the frequency domain. So we've seen in the past that rowhammer bit flips can compromise data integrity. And as a reaction to that, DRAM manufacturers such as Samsung and Micron deployed mitigations on their devices called target row refresh. These mitigations essentially try to estimate the rows that have been accessed most frequently and then send a preventive refresh before the periodic refresh happens. However, DRAM technology scaling has drastically reduced the number of hammers required by the aggressors to trigger bit flips, and this makes this estimation very challenging. Still today, there exists no tool or methodology that allows you to estimate how well these estimations work and to explore the corner cases. Today, I present you Blacksmith, a new tool that allows you to thoroughly assess DRAM devices. And we found with Blacksmith that TRR on all DDR4 and LPDDR4X devices in our test pool is broken. To get started, let me briefly introduce you DRAM and rowhammer. So here you can see a PC UDIM with 8 DRAM chips. Each of these chips is composed of multiple DRAM banks that are organized like a matrix. And to exploit rowhammer, you typically have 2 aggressor rows, here in red, and then you access them over and over again, many times and very quickly. This leads to charges that leak from the capacitors in the victim row that is in between those 2 aggressor rows. And then eventually, you will see a bit flip. It has been shown that rowhammer attacks are very practical in many different scenarios. For example, rowhammer is possible in the browser via JavaScript, on smartphones, and even over the network. It has also been shown that devices that use error correcting codes are vulnerable against rowhammer. So let me explain the rowhammer problem a bit more in depth from an attacker's perspective. So you have to know that DRAM uses the DDR protocol. And this protocol is specified by the Jattke standard and is a synchronous protocol. This means that all DRAM commands must adhere to specific timing requirements. One of these timing requirements is that each cell on a DRAM device has to retain its information for at least 64 milliseconds. And to achieve this, the memory controller in the CPU sends periodic refresh commands on DDR4 devices on average every 7.8 microseconds. And each of these refresh commands refreshes a few of these cells in a DRAM device. And this can be visualized in a timeline. So here you can see a refresh window of 64 milliseconds. And in between of 2 consecutive refresh commands, we can issue around 166 activations. So this means that an attacker has around 1.3 million of activations where they can spread hammering their aggressors. And what existing patterns do, for example, 6-sided patterns, is that they access the aggressors, for example here, aggressor 1, aggressor 2, and so forth, up to aggressor 6. And then this builds the first round of pattern execution. And this then gets repeated over and over again, for example, n rounds covering a whole refresh interval. Let's now switch the perspective to the view of the defense, of the mitigation. So I will now explain how a mitigation works, a deterministic one, but there are also probabilistic ones. So during normal activation, there is a component in the device called a sampler, looks at the DRAM activation commands and tries to estimate the row that has been accessed most frequently. So in this example, it would be row D. And then stores this information in a data structure. And then at refresh time, there's another component called the inhibitor that takes this estimate, so here row D, and then sends a preventive, so an additional refresh called target row refresh to that row before any bit flips can happen. And this problem of estimating the most frequently activated row is a well-studied problem solved by frequent item count algorithms. However, adapting those to DRAM devices is very challenging because in a DRAM device we have limited area, so we cannot have a counter for each row. Then there are these timing requirements that I mentioned before, and existing mitigations are deployed in devices lack a proper formal security analysis. Another point is that DRAM is becoming more vulnerable. So if you look back when rowhammer was first discovered in 2012 with DDR3, around 139,000 activations were required to trigger bit flips. The newer devices using DDR4 produced in mid-2019 only require around 10,000 activations to aggressors to trigger bit flips. And this potentially allows us to craft new attack patterns where each of the aggressors is hammered less than before. So we started our investigation by looking at existing Rowhammer patterns. So here you can see 3 examples. You can see a single-sided pattern where we have 2 aggressors that are far apart, the double-sided pattern that I showed before, and a 4-sided pattern, which is an example for an n-sided pattern with n equals 4. And we made the key observation that all of these existing patterns hammer the aggressors the same number of times, so with the same access frequency. And we asked ourselves if this is something that mitigations might have taken into account to facilitate tracking the aggressor rows. And for that, we wanted to know if non-uniformity can help to bypass Rowhammer mitigations. To answer that, we have designed 2 experiments. So in the first experiment, we take n-sided patterns and introduce some non-uniformity by replacing aggressors in random rounds by a dedicated aggressor pair. So here in this example, rows 13 and 15. And in the second experiment, we have complete random patterns. So we have random same bank rows that we access, and then at random rounds and random pattern locations, we access again a double-sided aggressor pair, here row 1 and 3. And we run these 2 experiments on the 40 test devices that we acquired from the 3 major manufacturers, Samsung, Hynix, and Micron. And here I present you the result of this experiment. So we compare our non-uniform patterns against n-sided patterns. And what we can see here is that non-uniformity is really needed on some devices to bypass the mitigations and trigger bit flips. So this is the first observation that we made, that non-uniform aggressor accesses can lead to effective patterns where previous n-sided patterns could not trigger any bit flips. Although this improved the results by around 15%, there are also cases where uniformity is needed to trigger bit flips. This is why we designed further experiment to explore which properties are important to build effective patterns. So we start with no assumptions and then gradually learn the properties that are important. I will now present the most interesting results from different devices. So the first thing that we wanted to know, when should we hammer an aggressor? And for that, we built the following experiment. So we have a double-sided aggressor pair targeting row 1 and 3 with a length of 1 refresh interval, and then it is repeated. And in the next round of the experiment, we basically shift this aggressor pair by 1 position. So we do 1 access to a random row of the same bank before, and then 2 accesses, 3 accesses, and so on. And what we observed here on DIM A10 from Samsung is that only if we hammer right before the refresh, we can trigger bit flips. And this is our second observation, that it's important to access the aggressors at the right time to bypass the mitigation. And here in this example, this can be explained by the mitigation, so the sampling might be less active or not active at all right before refresh. So this property and all other properties that I will introduce in the next slides can be mapped to concept of the frequency domain. So here the offset maps to the phase. In the next experiment, we wanted to know for how long should we hammer an aggressor, because if we increase the time that we hammer an aggressor, we potentially can trigger more bit flips, and this makes exploitation easier. So we start again with the same experiment setup as before, that we shift this double-sided aggressor pair, but now additionally, we try more intensities. So instead of just hammering it 1 time, we also try 2 times, 3 times, etc. And what we observed here on this device A10 again, is that if we increase the intensity, we can trigger more bit flips, but only up to a certain sweet spot. And then if we go over that sweet spot, then the number of bit flips drops. And this could be explained again by the sampler that might sample us too often if we have a too high hammering intensity and then sensor TRR before we can trigger any bit flips. And this concept can be mapped to the concept of an amplitude where a higher peak corresponds to a higher hammering intensity. And the last thing that we wanted to know, if our pattern should be longer than just 1 refresh interval. As I mentioned before, devices are becoming more vulnerable, and this means that we can build patterns that are longer, that hammer aggressors less time than before. So here in this example, we consider a pattern of 2 refresh intervals. So this means we also have higher hammering intensities that go beyond just 1 refresh interval. And then there are combinations where we end up, for example, here, where we only hammer every second refresh interval, but this interval with very high hammering intensity. And we made the observation that, in fact, exactly that is very important on some devices, like device B2 from Hynix. Only if we hammer with very long patterns and high intensities, we could trigger bit flips on these devices. And this property maps to the property of a frequency. For example, here, the frequency of a half would mean that we only hammer the aggressor pair 1 and 3 every second refresh interval. So from these 4 observations, we derived this property, frequency, phase, and amplitude, that we use to build frequency-based Rowhammer access patterns. But now the question is how to determine effective parameter values, because the parameters depend on the mitigation that is deployed on the device, and these mitigations are different across vendors and also on different devices from the same vendor. And we wanted to have a solution that is scalable, that allows us to test a large number of different devices, a generic solution. This is why we generalized our observations to these 3 properties, and an extensible solution. So if vendors make any change, we can refine our model. And for this, we built the Blacksmith Rowhammer fuzzer. And the idea of Blacksmith is the following. We have the frequency, phase, and amplitude that we randomize for the different aggressors in our pattern. And we do this in a way so that we have compatible values so that we can combine them into one pattern. Then we hammer the pattern and we check for bit flips. And then we repeat this procedure over again. I will now explain how this pattern building process works. So here you can see an example. We have 4 times 6 accessors in this simple example. And so we start with step 1, where we have an aggressor pair A1 and A2. For example, we choose the frequency of a half, so we exit only every second base period. Then in step 2, we fill up the same offset, but in the second base period. Now the amplitude is locked to 1, so we make this to simplify the pattern creation. And we could choose, for example, the frequency of a quarter. And then in the third step, we could add, also at offset 0, the aggressors A5 and A6, also with a frequency of a quarter. And then in the fourth step, we could add the aggressors A7 and A8 with amplitude of 2, for example, and a frequency of a half. And then in the last step, again, we would be forced to use an amplitude of 2, and we could have aggressors A9 and A10 with a frequency of a half, for example. And in this way, we craft the patterns. So we have different frequency, phase, and amplitudes combined into one pattern, which makes the fuzzing very effective. And we run Blacksmith on all 40 devices in our test pool, and Blacksmith found effective patterns on all 40 devices, which shows that TRR is broken. And we compared the results to state-of-the-art Rowhammer fuzzer Trespass, which only found bit flips on 15 of 40 devices. Blacksmith also found a considerably high number of bit flips on some devices. For example, device A17 from Samsung, there we found around 138,000 bit flips. This, of course, also has a significant impact on the exploitation. That's why we also looked into existing Rowhammer exploits. So in our paper, we analyzed 3 exploits. The PTE exploit worked on 30 or 40 devices, and we found exploitable bit flips in between 3 seconds and 2 hours and 8 minutes. For details on the other attacks that we also looked into, I kindly refer you to the paper. And to conclude the PC evaluation, so 100% of all devices in our test pool are broken, and the DIMMs are weaker than reported before. The high number of bit flips facilitates the exploitation. We also looked into LPDDR4X chips, which are used, for example, in smartphones and ultrabooks, and we also found there that all of these devices are broken. If you want to know more about this part of our evaluation, I kindly refer you to our paper. So this concludes my talk. We've seen that Blacksmith, compared with fuzzing and non-uniform frequency-based patterns, is a very scalable and highly effective approach. And we showed that all current TRR mitigations are vulnerable. Blacksmith's approach also generalizes well. So there was another DRAM vendor that we did not include in our evaluation that approached us and wanted to know if their devices are safe. And we ran Blacksmith on these devices and found bit flips in less than 4 hours, although we have never seen those devices before, so we didn't do any experiments and observations on them. And our work stresses that we really need principled mitigations with provable security guarantees instead of the obscure and proprietary mitigations that DRAM vendors currently use. And if you want to know how to design such principled mitigations, I kindly invite you to the talk of my colleague Michele about ProTRR, principled yet optimal in DRAM target draw refresh. Thank you very much for your attention.
Thank you, Patrick. Are there any questions from the audience?
So my first question is, thank you for the amazing talk. My first question is, have you tested multiple DIMMs together?
No, we only tested always one DIMM.
Okay.
Just because of the addressing functions, they are known for a single DIMM setup. This makes it easier. But in theory, you could also test multiple DIMMs, for example, to increase the efficiency of fuzzing. That's true.
So from my understanding, every single of these vendors would have their own proprietary TRR mechanism, right?
Yeah, and it even changes across different devices of the same manufacturer.
Okay.
But there is a kind of correlation. So we looked into applying all the patterns that we found across the devices on all the devices. And we saw that, for example, if we take patterns that we found on Samsung, that there might be one pattern that works on multiple DIMMs. So they are like golden patterns, you could say.
Okay. So I have one more question. Blacksmith requires a large number of things to be maintained in terms of timing. Like if you want to carry out this attack from JavaScript, will it be practical enough to keep a track of so many timing parameters? Like you have to get them correct, right?
Yeah, but we use side channels for that. So basically, you only put into Blacksmith the number of activations that you can do.
Yeah.
You can determine that with a side channel between two consecutive refreshes. And then Blacksmith generates a pattern that works with that value. And that during execution, you again use a side channel to detect when the refresh happens. So they are always aligned with the refreshes.
Okay.
So it should be possible. I think flushing the accesses from the cache would be the major challenge to realize it in JavaScript.
Yeah. Thank you.
You're welcome.
So, Alyssa Milburn, Intel. Have you tried the ECC-based attacks with this?
No, we haven't looked into that.
Do you plan to?
No, there are no current efforts in that direction, yeah. But it's definitely something that would be
I'd love to
interesting.
see it if anyone else is looking into this kind of thing. So, but thank you.
Thank you for a nice talk. I have a question to you. You said there was a vendor who approached you and asked you to study their devices. Were you studying their TRR mechanism, or you're studying their underlying sort of medium of how did those devices have TRR in them?
Yes, they also had a mitigation, and we did not include them because a small vendor, and they sent us some sample devices as ODIMMs, so DIMMs that are using.
So my question is, do they outsource this TRR? Like, how they're building their own devices? Don't they understand how their TRR works? Like, why would they ask you to study it to discover if it works?
Only to test if they're vulnerable, because they claimed in the DDR3 devices that they have a design that allows them to mitigate Rowhammer, and that's why they wanted to know if their DDR4 devices are also safe.
And did they share with you how their TRR work?
No.
Did you consider asking them, hey, tell me how TRR works, and then I'll tell you exactly the right pattern of breaking this? Isn't that sort of...
They're interested in the mitigation of my colleague Michele, but I think they did not share with us any details about exactly how the mitigation works.
Thank you.
You're welcome.
Okay, let's thank our speaker once again.